Now, the interesting thing about how Ethernet actually specs out to the OSI reference model is you'll see that it actually corresponds to both the physical layer and the data link layer. And really, it breaks out the data link layer into another sublayer called the logical link control layer. So you have the MAC sublayer and the LLC sublayer that's also built into this standard. And as you see, all the various different standards we have for Ethernet. Start with Ethernet 2 or DICS Ethernet, the original 802.3 standard. From there, they went to the IEEE 802.3 and then all the different sub-standards underneath it, 802.3 D and U and Z, which I mentioned, and AF and so on. But I also put on here token ring and FDDI for a very good reason. You'll see the sublayer, the 802.2 header. If you go back to the late 80s and even early 90s, there was a time at which we couldn't decide what was better, whether it was better to bridge or to route. The problem was if you were communicating between a Ethernet network to a token ring network, it didn't work very well at layer 2. You'd have to go up to layer 3 to make it actually function. So in order to bridge between a token ring network and a Ethernet network, they created another subheader, this logical link control header, the 802.2 header, in order to allow you to bridge between dissimilar networks. Technically, it is much better if you were dealing with those kind of technologies to route between the two because it was, well, a lot simpler to engineer. But the IEEE committee wanted to do it their way, and to do it their way, they had to create it and set it up to work at layer 2. So typically what you'll see is an 802.3 header with the subheader of the 802.2 snap header is what is also referred to it, that logical link control sublayer. It's also important to understand how Ethernet really works. It's a carrier-sense multiple access with collision detection network, which broken out into acronym form CSMA/CD. Now, what happens here is in a shared media, and that's what Ethernet's designed to do. In a shared media, if two devices try to transmit at the same time, it creates a collision, and both devices back off. There's a jam transmission that's sent out, jamming the network, saying, hey, two devices accidentally tried to talk at the same time. Nobody talk again until a random timer expires. So both devices set a random timer, whose timers goes off first, they start transmitting, and now the wire is free to use. Now, the problem here is this is with shared Ethernet, either a 10 base 2 or 10 base 5 coaxial bus-style strand, or a twisted pair connection going through a hub. Typically today we don't have collision issues because we're going through a switch and we're using technologies like full duplex. We'll talk about full duplex and switching mechanisms in the next section. But for now, let's talk about the Ethernet frame header itself. Now the Ethernet frame header, starting with the DICS Ethernet frame, starts off with a preamble. Now the preamble is just 101010 through 8 bytes. That's to indicate whether or not we have a collision in the network. If we have a collision in the network, the preamble will get distorted and we'll realize that there was a collision. We'll jam the network and set our back-off algorithm so that we can retransmit when the wire is free. From there, it leads with the destination header. Now the destination header is 6 bytes. That's a 6-byte MAC address, or 48-bit MAC address there, which we'll see the frame in the next section here. And then we have a 6-byte source MAC address. So the source Ethernet card that's sending this device puts its address in the source portion, and then the destination field is where we're actually trying to go. Then we have an Ether type field, and then the payload, which would be our IP address and TCP header, and so on. Could be upwards of 1,500 bytes as far as the payload's concerned. And then a 4-byte frame sequence check at the end to verify that the Ethernet frame is good. All right, notice the difference between the Ethernet frame and 802.3 frame is we changed the preamble from 8 bytes to 7. There's an SFD field there. There's also the potential in the 802.3 frame to insert that 802.2 header that we just talked about a second ago. Now, I should mention that the SFD, I didn't break out the acronym. Usually I'm pretty good at doing this, but just because I missed it, I'll make sure that I get it here. SFD is start of frame delimiter as far as the breakout of the SFD term there.